Hi, my name is Yi. I'll be presenting our work, Clobber NVM. Clobber NVM is a compiler-based high-performance PMEM library. This is a joint work by UC San Diego and CU Boulder. It's published on S+21. Persistent memory, such as Intel's Optane DC PMEM, is commercially available. Because it's byte addressable, persistent over power failures, and delivers DRAM class latency and bandwidth at the same time. It provides a lot of possibilities in a new programming model. But the cache is still volatile, and cached updates will be dropped after a power loss. So in order to actually use data in PMEM across reboots, PMEM applications need to ensure they are crash consistent. The most popular way of building a crash consistent application is to use a PMEM library, for example, PMDK. PMEM libraries allow programmers to apply sets of writes to persistent memory atomically. Unfortunately, those current libraries impose significant overhead. Take the list push function as an example. Compared to the DRAM program, an undo log-based PMEM program needs to first copy a value into undo logs, then ensure the undo logs are persisted by using memory barriers. Both impose significant overhead. So the question is, are they necessary? Think of this example. These are the read and write addresses of a transaction. When a power failure happens in the middle of the transaction, the state of data at its write addresses is unknown. They might be inconsistent. But if the transaction is re-executed after the power failure, any potentially inconsistent data will be overwritten. When the re-execution finishes, data accessed by the transaction is ensured to be consistent. But the read and the write addresses might be overlapped. In this case, when a power failure happens, some part of the data at read addresses will also be in an unknown state. The recovery process cannot simply re-execute the transaction because the re-execution will be based on potentially inconsistent data. Our solution to the problem is Clobber NVM. This is the outline of the presentation. We have covered the background and the challenges, and we motivated the paper. And now we're going to talk about the key insights behind Clobber NVM. Clobber NVM allows programmers to mark failure atomic operations with transaction boundaries. A transaction input is a value assigned before the transaction's execution and then read within it. A transaction output is a value written in the transaction and then read after it. You may notice that the size of the list is a transaction input and a transaction output at the same time. In Clobber NVM, we formally define this kind of input as Clobber input. A transaction input is a Clobber input if it may be overwritten within this transaction, and this write that overwrites the input is a Clobber write. Clobber inputs are a problem for execution. If an input is clobbered during transaction execution, re-executing the code will use a new value for the input. For the same reason, if a failure happens in the middle of a transaction, the recovery process cannot simply re-execute the transaction because the re-execution will then be based on inputs that are in an unknown state. Clobber NVM uses Clobber log to undo log before Clobber writes. Clobber log records the old values at these overlapped addresses. If the power failure happens in the middle of the transaction, data at overlapped addresses will be rolled back to transaction's original inputs by writing Clobber log entries to their corresponding addresses. When the transaction re-executes, it will only read consistent data. Re-execution recovers potentially inconsistent data. When the re-execution finishes, the data is recovered to a consistent state. However, things can be more complicated on current machines. We expect hybrid machines with both PMEM and DRAM in the near term. PMEM applications are going to access both persistent data and volatile data within each transaction. So on these machines, after a power failure, outputs in PMEM will be in potentially inconsistent states, and both inputs and outputs in volatile memory will disappear. To enable re-execution after failure, Clobber NVM uses another log to store volatile transaction inputs. We call that vlog. Vlog includes inputs that are stored on the stack or in the volatile heap. To enable simpler recovery, Clobber NVM transaction is isolated within a function. Usually, these inputs are function arguments. Clobber NVM also collects the function name within the vlog, because the function provides a convenient handle to initiate re-execution if failure ever happens. At restart, Clobber NVM first detects if there are any uncommitted ongoing transactions. Using the transactions logs, Clobber NVM restores both the volatile and Clobber inputs. It will execute the transaction from the beginning, continue to progress, until completion and commit. This is the key insight behind the system. In the next section, we're going to talk about the design strategies and their implementations. Clobber NVM's compiler is built on top of LLVM. We introduced 3 compiler passes to the compiler toolchain. The first pass identifies writes within a transaction that may clobber an input, then instruments the clobber log callback before the writes happen. Then the second pass adds callbacks to all memory accesses. These callbacks allow the system to intercept accesses to NVM, possibly do pointer swiftly. Lastly, the third pass instruments vlog callbacks to record the function names of the functions that isolate transactions and their arguments. We're going to cover the first compiler pass in this presentation. You can find more details about the other tools in the paper. The compiler pass is responsible for 3 things. Firstly, it conservatively identifies candidate clobber writes. The compiler pass relies on alias analysis to produce results that indicate 2 memory accesses cannot, may, or must point to the same location. But this analysis may not be precise and may over-identify clobber writes. So after this analysis, in order to reduce the logging cost, it's going to remove the candidate clobber writes that are not true clobber writes with further analysis. Lastly, it instruments a clobber log before each clobber write. The first pass conservatively identifies candidate clobber writes. It follows 2 steps. The first step identifies candidate input reads. The second step uses these reads to find candidate clobber writes. To find all possible candidate input reads, a read is not a candidate input read if it is dominated by a write, and its dominating writes must modify the same address. All other reads are labeled as candidate input read. In this example, read 1 is dominated by write 0, but read 1 and write 0 do not access the same location, so this makes read 1 a candidate input read. Similarly, read 2 is also dominated by write 0, and they may or may not access the same address. Because they may not actually access the same address, read 2 is also a candidate input read. Lastly, because read 3 is dominated by write 0, and they must access the same address, read 3 cannot be a candidate input read. The second step uses these reads to conservatively find all possible candidate clobber writes. The compiler identifies clobber writes for each input read. Candidate clobber writes include all successor writes that may write to the same address as the input read. In this example, read 4 is a successor of input read 1 and input read 2, but it will not write to the same address as the input reads, so it is not a candidate clobber write. Read 5 is also a successor of input read 1 and input read 2. It will write to the same address as input read 1. This makes it a candidate clobber write. Similarly, because write 6 is a successor of input read 1 and input read 2, and it may write to the same address as input read 1, write 6 is also a candidate clobber write. To reduce clobber logging cost, we perform additional dependency analysis propagation to remove candidate clobber writes that can never be true clobber writes with further analysis. We target 2 general types of false clobber candidates. The first type is called unexposed. This false candidate may be the first write to overwrite a candidate input, but if it does, it is provable that the input candidate is a false input. In this case, the input read is dominated by a write. Because the earlier write and the read may not access the same location, The read is considered a candidate input. The subsequent write may also access the bits location, and so it is considered to be a candidate Clobber write. But both writes are guaranteed to access the same location through alias analysis. So as a consequence, if the later write overrides the read cannot be a real input because it will be dominated by the earlier write. In this example, write 2 is identified as a candidate Clobber write in the previous step. But this analysis finds that if write 2 does not access the same address as read 1 does, it does not Clobber read 1. If write 2 must access the same address as read 1 does, write 2 will Clobber read 1. Because write 0 and write 2 must access the same address, read 1 must also access the same address as write 0 does. This makes it not a Clobber input, and thereby makes write 2 not a Clobber write. The second type of false Clobber candidate is called shadowed. A shadow candidate may indeed override an input, but if it does, it is guaranteed that some earlier write would have already Clobbered it. This relationship requires two conditions. Firstly, it requires some earlier write to dominate the shadowed write. Secondly, the alias relationship between the input read, earlier write, and shadowed write must ensure that if the shadowed write does override the input, the earlier write would have first. There are three possible alias relationships between three accesses that meet these conditions. For example, in the write case, because write 1 and write 2 access the same address, if write 1 does not Clobber read 0, write 2 will also not Clobber read 0. If write 1 does Clobber read 0, write 2 will Clobber the value produced by write 1, but it will not Clobber the original input. In practice, you can also find this kind of false candidate in loops. The first iteration Clobbers the input, but subsequent iterations do not need to log, because in these iterations, the Clobbers the value produced by the previous writes. After this analysis, the compiler plans instrument Clobber log callbacks based on the analysis results. So these are the designs and implementations of Clobber NVM. Next, we're going to show its performance. We run the experiments on a platform with two 24-core processors, with 192 gigabytes of DRAM and 1.5 terabytes of Intel Optane DC PMEM. So Optane DC PMEM is set in 100% AppDirect mode. All experiments use ext4 DAX to manage persistent pools and directly access PMEM pages. In our experiment, we compare Clobber NVM's throughput with PMDK on 4 data structure benchmarks. The benchmark populates each data structure with 1 million key-value pairs. We find that because PMDK undolog shares the same logging subsystem with Clobber NVM's Clobber log, and it usually needs significantly more undolog entries inside each transaction, Clobber NVM shows about 1.8x of its performance on average, and can perform up to 2x compared to it on HashMap and skip list. Next, we compare Clobber NVM with IDO. IDO is a state-of-the-art recovery via resumption library. Its compiler pass breaks transactions into a series of consecutive idempotent regions and logs at the boundary between idempotent regions. If a failure happens during an IDO transaction, IDO re-executes the interrupted idempotent region and resumes the remainder of the interrupted transaction. Because its code is not publicly available, we re-implemented a compiler instrumentation path to instrument the code and collect transaction information as IDO would have. IDO places the program stack in the persistent memory to avoid manually copying stack variables into persistent heap on transaction initialization, but it instead needs to track accesses to stack variables during transaction execution. The log entries at each boundary require a snapshot of most registers and flush and fences for any modified memory locations. Because of this logging strategy, IDO persists more data at the boundary of idempotent regions compared to Clobber NVM. The strategy generally also incurs more logging costs than Clobber NVM's logging of Clobber writes. Clobber NVM only needs to log when a write clobbers a transaction input. On the contrary, I-do logging needs to log whenever a write clobbers an idempotent region's input, and not all region inputs are transaction inputs, as they may be intermediate state local to the transaction. Our evaluation shows that it logs 1x to 23x more frequently compared to Clobber NVM, depending on the specific data structures and workloads. On average, I-do logs 4.2x more bytes compared to Clobber NVM, and it can uplog to 7.2x more bytes on skip list. We also experimented memcached with 4 types of workloads, ranging from insertion-intensive to search-intensive. The insertion takes from up to 95% to 5%. Clobber NVM outperforms PMDK animosity on all workloads. It outperforms PMDK animosity more on more insert-intensive workloads because both of these libraries require more log entries. And we find that Clobber NVM provides up to about 2.5x of animosity throughput and 1.8x of PMDK throughput with single thread on 95% insertion workload. Lastly, we'll show performance improvement by avoiding redundant Clobber log on the 4 data structures and memcached. On the 4 data structures, skip list shows the most performance improvement of up to 15%. We find that the compiler path removes 2 Clobber candidates out of 5, end up requiring only 3 Clobber log entries per transaction. On memcached workload, the one consisted by 95% insert and 5% search requests improves the most. The improvement is up to 15%. As can be expected, the avoided Clobber log entries are on the write request path. The unoptimized version incurs up to 32% more Clobber log entries and 47% more bytes. Here, we conclude the paper. Clobber NVM is a system that recovers by re-executing interrupted transactions. At recovery, interrupted transactions restore inputs using Clobber log and vlog, then re-execute to the end of the transaction to reach a consistent after-execution state. Clobber NVM uses compiler analysis to identify necessary log entries and adds logging callbacks for selected variables, including Clobber input addresses and non-local volatile variables. Our evaluation shows that Clobber NVM significantly improves performance compared to state-of-the-art failure atomic libraries. That's all for the presentation. Thanks for listening. You can find more details about the project in the paper.